Welcome back to High Performance Computing. This is the second part of Lecture 6, Parallel Programming with OpenMP. So in the first part of the lecture, we thought a little bit about moving from distributed memory programming to shared memory programming, and that's what we basically had done all over the course. In the beginning, we really focused on distributed memory programming with message exchanges and MPI. So in the first part, we really conceptually established that basically shared memory programming is different. We communicate, so to speak, through the memory. There's not an explicit message exchange in a way, it's just read and write to the shared address space. And this enables us, of course, high performance. As you know, that memory is a very good and very powerful and performance-wise very good to use. And with this, it's much more efficient to use shared memory programming with OpenMP, basically within the node where you have a shared address space instead of using it with MPI message exchanges within the node. However, we also learned, and we will establish more in the actually following lectures of lecture 7 and so on, when we basically then think about combining both, right? So basically you would think about that OpenMP obviously has limits. If you can only do shared memory and then be within a node, you don't really come far. You wouldn't call it high performance computing. But the key idea, what many people use, and we had the example of our HPDBSCAN algorithm, for instance, we basically use OpenMP within one node that has a shared address space. And then basically we use MPI to do the communication between the nodes. And with this, we have full power with basically access to memory space to speed up things. And then basically, of course, to have a more aggregated way of memory possibility and programming possibilities across nodes, we use then MPI message exchanges to get the data across. And of course, then with this hybrid approach, as it is called, you can scale up very highly. We also have seen, of course, it's here and there challenging to do so, and there will be performance issues. We will talk also in one of the next lectures around, but still you can achieve almost near linear performance here and there when you scale up. And of course, it depends a bit on the application. So at some point in time, there will be a tail off, because then, of course, the message exchanges overhead will taking basically more and more of the aggregated bandwidth and so forth. But so these are things which we will discuss later. Now, the part of this lecture here, we want to learn a little bit more what OpenMP is about. So more from the idea how you really program it. The first part was more conceptually establishing it. So let's have the second part a little bit lower in terms of codes and also in the idea of how we really program it. So the first thing you have to really think again is, of course, thinking parallel. That is an important part of the course, as you can imagine, enabling us to do high performance computing. And what we see here is a little bit how the situation works with the master thread here being basically kind of spawn more or less here from these kind of processor that then in turn basically spawns different team of threads. And we also learned that the master thread is basically a very important thread and is almost always existing. And the interesting thing is it remains basically a sequential programming language, how we do it. As you remember, we said we just add here and there, then in the sequential programming, just compiler directives to denote parallel regions. And of course, then the threads will work in this parallel regions and working on some nicely parallelizable problem like loops and so on, what we will look in today. So interestingly enough, how you really program it is usually that you don't really assume a certain number of threads. So in order to achieve scalability, you will keep that a little bit, let's say, open, because of course it depends what really you can use on different systems. You can have your application ported to another HPC system, and this has maybe much more powerful nodes, so you can have more threads, etc. So in the end, you would do it like this in a main, let's say, C program here as an example, where you do now the printf statement, and this is the hello world for OpenMP. And of course, we show you this next time in our practical lecture 6.1, how that really works. And in your assignment, you will also play around with this a bit. But you see here in this Sentinel, in this pragma statement, I don't say how many threads are really working now on this parallel region. Instead, I have in the job script, as I showed you also in the conceptual part about HPDBSCAN, already the OMP number of threads here inside. And this determines then, when I did compilation and then executed this hello world program, that it will be 4 times getting out here. So the way how it works would be, I have the master thread. It's always a kind of T0, so he remains active. You remember the line I have showed you the last part, right? That always keep constant, but it's not that the master is just the manager, so it becomes part of the working force as T0 here. And then basically, of course, spawns as many as you have here, keeping, of course, the master thread in itself as well, being part of the team of threads. So, and then, of course, doing the hello world 4 times. So this was the simplest program. Let's do it a little bit more elaborate, how we basically would move from a C program to the real hello world example of OpenMP maybe. So first of all, we have to have the OpenMP library, of course, with the API definitions, with OMP header here included. And the interesting thing now is, and connecting it a little bit perhaps to MPI, if you think about it, instead of ranks, we have here the thread IDs, right? So this will be an important factor, that basically every thread has, so to speak, their own thread ID. And we have here 2 types of variables we want to use. The shared variable, which is the number of threads at all, and then of course a local variable, which is the thread ID. And the thread ID is really something which should be then private to each of these threads. Because think about it, what now happening is that here's one master thread, he is doing this. But of course, all of these different threads which should be coming out here, the 4 that we discussed, for instance, of course, they need variable space to include this thread ID. Almost like we had with rank 0, you know, rank 1, rank 2, rank 4, etc. This will be a unique identifier. And of course, to store this in different variables, we need to know actually and have space for it. That's why basically we have this private, not shared local variables. And then we basically get here the thread number almost as we got the rank number from the MPI engine, the same way we get here the thread number, which is essentially then you know, your unique identifier of the different thread. And in order to identify the master thread, as we would have done in the basically in the MPI space, when we did if rank equals 0, then do something what others don't do, you can do the same thing here. Just use the thread ID, and then, for instance, here you see we want to have only the master process telling us that the number of threads in this parallel regions are essentially this number of threads here, and basically the OMP standard gives you also this get number of threads here, essentially also the function for it to get all active threads in this current parallel region, which is denoted by this pragma and by this bracket here. So basically stopping here and then on join, of course, this would be all not any more accurate. So of course, the practical examples that I do in the next basically lecture and also your assignment were basically focusing on this. So then you get a bit more hands-on experience, but you already see that here we don't specify anything how many threads there will be in the game. That is of course coming then, as I said earlier, in the batch script. And the idea how you could basically then think about it, it is almost similar, like of course MPI, in the sense of essentially loading this, the kind of compilation step that you have there. Obviously, you have to basically link to specific libraries, which you see here a little bit in this example. You have the GNU compiler here and hello threads out of the C program. So the step still basically remains, but you have to tell basically the GNU compiler that they actually compiler directives for OpenMP inside, and then you get your hello threads executable. So also here we go from a valid C program to a valid OpenMP program that you see here with OMPH. Another example, which is a very trivial example here with OMP parallel. And still, this is now a very general program where you see it's also scalable in a sense that you can always say, I increase the number of threads, and I would be basically having still a correct program, scaling up, and have, let's say, more output, essentially, given this pragma MP parallel. You see also there are no brackets here. That means essentially only this is executed in parallel based on this pragma statement. So in a way, so far, relatively similar to MPI. But of course, now the power of OpenMP is this work shoring constructs that would think is a very good thing to do when you have some specific part of the application which is very often used in terms of programming. One is, of course, when you think for loops or do loops, whatever it is, they capture, let's say, a lot of application logic usually. There are many loops usually in all the different scientific and engineering applications. And perhaps here and there, there's a chance of really parallelizing them. And I give you some examples on it. So you would say, instead of explicitly program that, could we not automate the process? So you just do a pragma statement in front of a loop, and then essentially the idea of the loop will be then parallelized. So, and this is what we want to achieve, and we can do this. I show you later. Another idea is, instead of, let's say, doing this, you maybe want to have more, instead of data parallelism, what in a sense the for loop would do then with different data items, maybe in an array in a loop. What about if you have more functional parallelism? So then you can fork different sections in the OpenMP environment that may be responsible for different elements still executed in parallel. So what that could mean is, one is maybe doing the boat movement, one is doing the wave height calculation, and the other one is basically doing essentially the wind speed calculation or so. So different functional parallelism parts, which we then join later in order to go maybe to the next time step in the ocean simulation, and then again and again. And of course, maybe here and there also the master thread will do MPI and then communicate with basically another node. And inside that other node, you would do the same idea of having this kind of sections that breaks the work then into different parts. And for some interesting serialized parts, which are sometimes necessary, it makes sense to also use the work sharing construct, which is a bit funny name for it, because in the end, you have just, again, a single thread doing some computation here. And we show also later some examples on that. So these are examples of these OpenMP work sharing constructs, which are now basically giving you lots of functionality, while the programming of those is relatively straightforward. So you think about now, oh my God, I have to do hell a lot for this, to do all of this forking and all of this joining and then creating sections and so on. But here really the OpenMP standard comes to play in the environment and the library of it by using really in front of loops just one statement to really parallelize a loop, or one statement in front of each of these sections here and so on, to just basically think a little bit about, of course, the data and the variables, as we have already had in the hello world, right? This, thread ID, for instance, should be a bit private, because each of the different threads need their own instance of the thread ID in order to store, of course, then essentially the value for the thread ID, while some of the other parts could be shared, like the number of threads, which is, of course, for everyone the same within the same parallel region. So let us look a little bit on one of these application examples, which admittedly are very simple, but still captures the essence how nicely parallel you sometimes can do this. And here you see nicely parallel and independent of each other. This goes into one notation really. And here you see a good example of this. If you have, let's say, a normal loop that you would do here from 1 to 1000, and you have some calculation to do in this index, right, where you loop over all these 1000 iterations, and you just multiply a constant with another array, also with the same index. Now, immediately what comes to your mind is that they are all just actually having a constant multiplied by some other element in the array. So in other words, here we see that the array part in each of these iterations is the computing is completely independent of each other, right? It doesn't matter if you would combine first 1000 and go lower to 1, or you do first 1 to 1000, because you have only dependency on the current index. It's nicely parallel. And by just multiplying it, for instance, with a constant here, is even more easier. So it actually could be possible to, as a, let's say, very small scale example here, to break this big loop from 1000 up into 2 chunks to 500, and then another one from 501 really to 1000. And this is what essentially then this MPI, the OpenMP directive will tell you. If you put it in front of loops, it will break down the loops into different threads. Then really that basically meaning that here the thread runtime really of having these 2 threads here used instead of just 1 thread, this would be basically some speed up. This is more conceptually, and of course, when you now think about how that looks like in a more elaborate example here, maybe it still captures the same essence of being, so to speak, independent in all of the loop elements. While we learned here in the previous example, the multiplication, let's assume we have an application logic just adding here these 2 vectors. And if you know a little bit about this, the color coding shows us again how we actually do this. And in order to get the new X, of course, you see, we can do this nicely in parallel depending on the color coding here. So you would maybe cut that into 3 different parts. You would keep, of course, a private E for every of these threads coming here, because essentially we need that in order to get to the different array indexes, right? So private E0, private E1, private E2. And this is an important part. However, the overall array that we basically use and want to have access to can be shared. There's no problem in this. I just have to make the index right here. And with this only statement, basically, which is a little bit a simplified demo code here, but still in terms of OpenMP, there's not much more you need to do. And of course, include the OMP statement, right? And allocate variables a little bit. That's what we do in C. But in the end, the real parallelization that you introduce is just this small pragma statement. And each thread works then independently and basically works then on this kind of, results in the global array, on the shared array, by using this private E as the own index, so to speak, while you don't program any of this in parallel, right? It remains, so to speak, a more serial way of programming, but you just give the loop here the command, please break it down into smaller pieces, and the OpenMP engine will actually do this. And that will be then looking a little bit like we have here on the top, that, we have this different threads really as an example, and they have the shared data, which would be then the shared array here, for example, where you can write and read from. But everyone has also private data, which is then, for instance, the index, that here is the E. And then, of course, you can scale this up. You have here E, that is for each one differently, but the number of threads, of course, will be then coming again outside from the job script, and is also not here basically implemented in the code. Now, of course, there's some fine tunings that you can do. And also, if you think about that, of course, some threads might be faster ready than others. You can have different schedules, as we call that. So let's move and look into this a little bit more in an advanced for loop example, where you have still the idea of a loop here, and you see the index is still dependent and nicely parallelizable because it doesn't depend on any other, let's say, index before or after. So here we can do a nice pragma OMP, and it will actually do now basically a chunk-based cut of this kind of loop in terms of basically scheduling it in parallel. You see that a little bit shown here. Let's assume we have 4 threads where basically the chunk represent this part here, saying of how much I really should have a sized piece. Maybe it's not smart to doing it really always, for just one E. Maybe you want a collection of those into basically and then parallelized. You also see that when this one thread is basically finished, you basically see here a very static mapping of the chunks between the different threads here. And here a dynamic, really the first thread that is ready, get then the next part assigned. You see thread 1 is here very fast, so it can be directly assigned again to some chunk in the loop in order to really progress. And with this, it makes also sense that basically there will be not synchronization maybe, because here you want to keep it basically very dynamic and agile. And so you put a no wait. That means that basically there will be no big synchronization at this, at the end of the loop. And this is just one example how you can quite fine tune the parallelization step a bit. And coming to the larger picture, of course, this is now the whole pragma block here. You can combine blocks in blocks, where already you clarify a little bit the situation about, of course, the variables you're going to use in this, because this would be not enough. You have to also specify a little bit what's happening with A, B, and C. The chunk, of course, the size that we define here on the chunk size. Let's say here we do 100 as an example, but it's something, of course, what you want to maybe understand in order to do now, let's say the loop 2000 here, which we have with n, not with every little e. Here you would say you combine some of these chunk sizes. Right, and then of course, as we discussed earlier, the private e again is important to that everybody knows where in the loop they are, all these different threads, while they're actually combining then for their certain, let's say, part of this construct here, then the array, and basically can modify the index of which is of course for each thread then a certain part, which is determined also partly by the chunk size. So I think it's more conceptually speaking here. So I think when you do the hands-on and when we have the demonstration next time, when I show these running example with some proper code, then it becomes easy to mind. And I think that's pretty clear. Here's an example of the so-called kind of sections work sharing construct, where here it's not anymore just about loops, essentially. Let's say there are different loops, right? I gave the example of boat movement. I gave the example of wind speed and wave height calculate. Could be all different functions or physical formulas behind it as one example in order to calculate things differently. And of course, these sections are independent, as this picture suggests. So there's no message exchange here between those basically sections. And with this, you have these blocks here really that you do as the pragma OMP section within the pragma OMP sections part. And here can determine that this will be, of course, and also basically something which will be split up by depending on the number of threads that you have really available in your thread team. While, of course, the master thread will take one of these sections for sure. And I think this is basically self-explaining a little bit. It goes without saying that we still have to, when we work with this interesting different, let's say, indexes here in the for loops, we still have to make it private because we have here different threads running into, and we really need to make sure that they all have their own private space of storing this. While A, B, and C, you see here we play again with this different arrays, basically, and D and C is computed with different parts of the formula that makes a functional parallelism now, right? It's not exactly equal. You notice we have plus and we have multiply. So in this sense, it would be, let's say, a fake here of different functions you really would compute, just to show you a little bit how these pragma OMP sections would be computed. Still, it is powerful because in the serial world, you would have first the addition and then the multiplication. And of course, what's happening here is now with the parallelization that we can do the multiplication and the addition here, both of these sections in parallel. Right, and then there's the idea of course, synchronizing a little bit, because by now you should say, we have basically this kind of shared address space and I can read and write anytime. Isn't that dangerous? And some of you maybe know from other courses, yes, it's very dangerous. We call that race conditions of some variable of sort, right? So this means because it's a shared address space, it can be basically set at the same time, so to speak, concurrently by different threads. And then when you have this concurrently, then of course there will be here and there the one that is basically catching the first and editing the value will be overwritten by the other that is a bit slower. And this is of course not really nice behavior. That's why if you have certain element in your parallel application that require to maybe, in order to write the variable, you have to read it before and then modify it with some certain aspect. it is good to put it in a pragma OMP critical region. And I modeled this here as a very, let's say, very tiny example, right? Here, if you have 4 threads coming here and basically they share all the X variable, obviously this is a problem if 4 threads doing the same execution. So some thread is basically lucky and has already the +1 from the other one, while the one that is here waiting for executing this basically has now the full picture, because the OMP critical will prevent any other thread to go in. So only this one thread is allowed to actually compute this. And inside this critical region, this is basically then something which is blocked for all other threads until it's finished. So at any time, this critical block is just accessible, so to speak, then for reading, incrementing, writing X here at any time. And with this, you have the problem that you see here a little bit explained, basically a little bit solved. So you either wait until it's properly written and then out of the critical region so that someone can properly write. In a way, of course, it hampers performance a little bit. If you think about that, of course, it's pretty similar like you see here with a single statement, that all the other threads are waiting, right, and cannot go into this, so they're blocked to continue. And with this could be, of course, getting to performance bottlenecks. But in terms of the correctness of your application, you really need these critical regions for some sort of updates in your physical formula and variables. Very similar in a way is this pragma OMP single. Also here, you want to prevent that others are actually doing something. So you basically put them as idle, right? So you put them more or less not really to sleep. It's really a difference between sleeping and idle in this sense. And once is this basically completed, we're basically meaning that the first one that is actually able to make it, this first thread will also then basically do this work that is inside here, while the others are idle, don't do anything, but they also, so to speak, not really waiting and then executing. They basically then continue afterwards, basically then with all the other threads and wait essentially until the single has really done this work and then join the work again in the team. So slightly different than the OMP critical idea here, of course, that basically here you have really just something which needs only one to be executed and not many. And this is another idea of a synchronization construct that we have in OpenMP. And there are different ways how you can, of course, now modify the behavior of these different, let's say, pragma statements. And one is very powerful that I want to give as an example, but obviously the OpenMP standard gives you lots of possibility that we want to basically explore here and there, but we need a full course in just on OpenMP, what we cannot provide here, because we want to also know about more other things in HPC. One powerful mechanism is the ThreadPrivate directive, which enables you a persistence between the different parallel regions. By now you can understand that you have, let's say, still the kind of serial way of how you program, and every now and then you would do pragma statements in order to parallelize something. Now, if you again need the space really for the variables and the values that you assign to this in also the other parallel regions, it would be, of course, bad to read and write again and so on from different, let's say, variables. So keep them as thread private is something what we enable here in the application example. You also notice I left out B here, right? So it's thread private is just A and X, and that will be an important factor when we understand what's happening here. We basically turn off the dynamic threads here. That's what we already had before, but it gives you kind of a difference from a private variable now, because when we set it once, we have here another parallel region, which is the first parallel region, and a second one later. But in the first parallel region, we have private B and the thread ID. So that is basically something which we also want to have in order to set it in all the different threads. And we see also we use A here, which is thread private. We set B with the thread ID, which is basically not thread private, just private. And then essentially we send X here some values based on the thread ID. It's not so important. But the important part is that actually A and X are thread private. So these values that we assigned here with A and X should remain relevant in our second pragma parallel region, right? And here you see we get again the number of the real thread ID, but we also give an output of A, B, and X at that time, right? Like we did before in the first parallel region. Now let's do this one in the second parallel region, and you see, you notice we don't assign anything. So A, B, and X are not reassigned, but we give them basically out here to understand what the difference between thread private and private means. So let's go and see a little bit now the output, how that would be running. We have the first parallel region, no surprises. We have 4 threads as an example. Also here, notice I never programmed that, right? So this is again coming from the MPI environment, when everybody here gets his own thread ID. That's what we do here in the first output, thread 0 up to 3. And then we have A, B, and X and its values. And we see that A obviously is a thread ID that works. B is a thread ID, also works. And then I do some magic here with X, which doesn't really matter. It's just a multiplication and addition of sorts. But the point is, it will be the same basically and kept for the next parallel region. We collapse here and do a join again, because the parallel region, the first one, is over. Then the master thread is doing maybe some serial work which is needed, some IO or message exchanges with MPI, whatever. But in the second region, we now experience a difference. Obviously, with the thread ID, we still have here our private variable. So that enables us to, again, of course, say here thread 0312. And the A and B and X is not set. So let's see what's left over from the parallel, or the first parallel region really, which you see here very nicely. The A was thread private, so it has still the values we had above. And suddenly B has just zeros, because basically it's a new variable that was just private in this particular small parallel region, and is dropped then, of course, in the second one. So, and X again, because being thread private, keeps the same values. You also see that if you do the output, it's not always deterministic, always set 0, 1, 2, 3. You see here basically a wild mix usually on when outputs will happen. But the key message to take away is that the values at least are still accurate for all of these different processes if it was thread private. And there are many of those ideas how you can really basically influence a little bit the parallelization of it, and really fine tune a little bit, that you see already here with the static scheduling as an example again. The vector dot product example is another interesting example, because here we can introduce something which you already know a little bit from MPI, perhaps, if you remember the MPI reduce operation. This is an operation that is often used and obviously in shared memory as well. So that's why also the reduction clause basically in pragma has also these functionalities. If you remember, the reduce operation was, let's have simple operations already with different, let's say, threads here in order to compute directly some form of a result. So in a way, a sort of analogy with MPI reduce, but of course in MPI reduce, what I did was really message exchanges between the different processes. And here I have just, let's say, some simple math calculation of the memory spaces involved here in the shared memory programming. And you see how that works basically for this pragma statement here. We say the reduction clause should be adding up the result in order to make the final result of all of those happening, which is essentially interesting, because here we have this vector dot product, and what is coming out of this, as you already know, is a scalar usually, and so you can easily basically add this here up. And by doing this, of course, here in parallel, this means the result here would be still only the result in parallel computed and missing the global picture. But with the reduction statement, you can basically then, when this is all finished, or at the end basically of the loop, can see that the final result has been actually added up to the global result. And I think when we have this application example really running, then it becomes much more obvious, and this maybe one slide can directly show you. Still, the same goes with the idea of the schedule here, static and then chunk-based, as we had before, in order to not really do every E here automatically and chunk it to the process, to the threads, because this would be quite some overhead, right? If every thread would just have one E and then goes to the next, another E goes to the next. So here we chunk again some of those together. And you also see that, of course, private is something what we want to keep. And we reduce really of the result here at the end so that we have the global picture, that basically this loop construct will add all the values up to remain in the serial part. Then, of course, accessible. You see that we basically going here then with the end of this pragma section again, basically to the general master thread, because essentially you have this pragma statement in front of a loop and not really in front of a bracket. So it means only the loop will be parallelized. And since we have a result reduction here on plus, we basically have even in the master thread that follows the parallel threads here, the result that is a global result that we also wanted from all the different threads working in parallel. I hope by now you can follow here and there these examples. And again, when we do some more elaborate examples in the next practical lecture 6.1, I think it becomes easier to mind. Here's another very nice application example where you can also see the power of parallelization again, and also something which will be in lecture 13 more explored, called Monte Carlo methods, which means a bit, if you repeat an experiment often enough, you can basically refer something or basically get some information out of it. And here, this is an example which is quite similar, where you think P can be actually approximated. And by doing this in parallel with enough, experiments, you see that a little bit here of counting the hits basically within the radius and the total number of random points you basically put here to this part. And of course, you can, with the distance from the origin, determine if you are in the radius or not. So then you basically, with this and doing this, let's say long enough, as you see here in the picture, this repeated random sampling, so to speak, you actually get very close of getting to the true value of P. It just takes, I don't know, lots of random runs here. And of course there, when you have this lots, as I say, the number of runs, which is nothing else than a for loop again, right? To do the for loop and for loop, and to basically then understand a little bit what's happening when we basically hit the radius. You can basically do this in parallel, because in the end, you just do random repeated sampling here of the data or of the points. And this is not dependent on the time step before, so to speak, on the loop before. So you can nicely parallelize this and speed up this. And I think this is a very nice example how people use this also in science. And we will talk more about the statistical principles behind random sampling and also Monte Carlo methods more when we have lecture 13. So, but this is of course something what you also can do with OpenMP here in this particular example. Of course, then we will think about that even of OpenMP, we should think about more patterns and more logic when we want to use it for some real scientific and engineering application. Of course, the Jacobi 2D application that we had for the heat dissipation in the room, you remember here after so many time steps, can be done with OpenMP as well. And of course, there we also have to think about, when we think about address spaces, shared address spaces, that we need the data from the surrounding parts of the stencil here, or of the grid really, and also need this for the next time step. So basically, this is something which we will also see then and combine with MPI that we had done before, and see how that works in a hybrid fashion. And it's coming. And then perhaps at the end, a little bit also some comparison with MPI. Now you have understood that actually MPI ranks are very similar than OpenMP threads, but of course are different. MPI ranks are full-blown thread processes, while OpenMP are lightweight threads. We have rank 0 statements that we can use here for if statements as I would do it with a thread equals 0 ID. So also here I can influence the application logic with basically having a unique thread ID, like I have a unique MPI rank. The most key difference, however, then is the interprocess communication in OpenMP, which always says I have the shared memory space, basically, while here in MPI, basically I'm always sending messages over the wire from one process space to the other to get access to the memory or to really send the data over with buffers. Here, of course, we have, let's say, the data exchange through the memory, and basically with this, with shared variables. We can see still we have synchronization statements, something similar like MPI barriers that we have seen, or this automatisms like the MPI reduce operation, which is of course close to the idea of the OpenMP reduction. Still also think about that, of course, load imbalancing can happen, basically with different parts, especially if you combine in hybrid programming, and what we will also then look in one of the later lectures more into detail. Finally, there will be one lecture where you, of course, think about, now that I program all of that, what I can actually do to debug all of that and to see the memory space really, and to look into what values are currently in memory, especially if you have this iterative behavior that we learned in the stencil methods, and then, of course, maybe doing it in a hybrid setup with 200 nodes, and each of these nodes have 8 threads or so. You immediately come to a large scale application. And for this, you need automated tooling to really understand it, performance analysis programs that we will look into lecture 8, which also can work nicely with shared memory constructs. And then perhaps as a next appetizer, then how you would do it with GPUs, you have this OpenAC, basically new standard, if you will, which is a little bit similar than OpenMP, but now enables basically also to work with accelerators. It would look a little bit the same way. You have OpenMP with a fork, the parallel regions to the join, and here you do the fork, but basically put it to a device like a CUDA device with NVIDIA GPUs, and then join back to the master. And the idea of using compiler directives is almost the same. You have to think a little bit of copying the data into the space of the device memory, if you remember, through the host memory to the device memory in order to do some calculations there. But also there, with lecture 9, we will talk much more about this when we look at this GPUs more in detail. And then, of course, basically, we will come back to our example in this kind of clustering where we have MPI, and for the local DBSCAN, we can actually use OpenMP a little bit within the node, and then come to this nice scaling behavior I already was mentioning here, and having a better simulation or better analysis really here in this cluster algorithm, but of course requires also much more thinking of how you break the domain basically into different pieces, and then how you deal it with the local DBSCAN and so forth. We have also learned that you influence the number of threads out of the job script. That's here again the example in the data sciences, where then basically in the source code of HPDBSCAN, you will see exactly this code, where we not only use OMP here, so do OpenMP, basically within the local DBSCAN run, which we assume then within the node, and actually then working on the neighboring points. And basically the real detail here is of course a bit abstracted, so there's some missing code here, and it's not important to understand that for you, but you can imagine that we do basically OpenMP for a local DBSCAN, and then to get really large scale, we every now and then can also go with MPI statements across the nodes. And that is what we will do in lecture 7. But it also is important to realize that these production applications really still rely on the idea of someone saying them outside in the job script, how many basically threads I have, depending on the job script, because I also need to specify how many number of tasks per node and so forth. And that's all I wanted to leave on the table for you in this part of the lecture. In the second part, we have a very small, tiny demo here still of a ray tracing, where you increase the number of threads. And with this, basically see that the ray tracing will be much more, let's say, fluent working. We see a really not nice performing ray tracing. It's kind of hopping and slow. And even if you give it more priority, it's still one CPU only. And basically doing this will be now enabling us perhaps more and more of these processes sharing the work, and with this coming to a much more fluent behavior later. And this is what you can do essentially with OpenMP. Even if you would think it's still just one computer, just one processor here, which is a laptop simulation maybe, but it captures the same idea of parallelizing it with a number of threads and tasks that actually make it work. Then, as you see here, with the domain decomposition 4 now is already much more faster computed. And of course, you can do now, as you see nicely in this basically video here, this grid is going more and more fine-grained, meaning more and more threads are put to the problem by just increasing the number of threads and tasks for this application. All right, so I think the rest is now obvious, and we don't need to look at this the whole time. So let's see where we are in the slides. Basically, we are done for now, some bibliography, and we basically will do some practical examples of what I just told you the next time. See you then.